You know about intervals of convergence as we gently entered into the field using the geometric series, but now we're going to use the intervals of convergence and the ratio test. A quick reminder, very informally, the ratio test says we're going to examine the relationship between a future term and its previous term by doing this fancy limit. You compute this limit and you come up with a number. That number is a way to quantify what's happening as you compare a future term to a previous term, or what's happening to the trend of terms as you cruise along your series, or the sequence of your series. So if we end up with a result here that is less than 1, we're going to conclude convergence, and informally what we're saying is your previous term is larger than your future term. It's more complicated than that, but that's a very intuitive way to look at it. And we're going to concentrate on this one since we're working with intervals of convergence. So here's the star of our show. We have this series, and we want to know the interval of convergence, which means basically this. If I could randomly be selecting any x values that I want, what is the interval of x values that will cause this thing to be convergent? And if I use the ratio test, what I have to remember is the ratio test is going to conclude convergence if the result of my limit calculation is less than 1. So how can we combine this statement and this big honkin' series into some calculus? Here's how. This is the ratio test applied to this series. This is a future term, meaning it's an n plus 1, it's an n plus 1, it's an n plus 1. So that represents the next term in the series. Then this would be its previous term. So I'm really doing the limit as n approaches infinity of a future term divided by a previous term. And what I want to find out is what x values make this result in a conclusion that is less than 1. That seems like a possibly impossible task, but algebra and calculus to the rescue. I'll spotlight a few of the moves. Anytime I have a fraction divided by a fraction, it's smart to consider turning it to multiplication by the reciprocal. So this thing's reciprocal is written there. And so now I still have to calculate that limit, but I have a way to help your brain deal with all this chaos. What I want to do is I want to match up, I can't use the word like terms because that's a math term, but terms that are similar. So I think you probably see what's going on. This is an x to the n, and this is a version of an x to the n, so I'm going to have them paired up. And I can do this because the entire denominator is all connected by multiplication. Same thing with the numerator, so I can change the order of multiplication if I'd like. This is a 2 to the n, and this is a 2 to the n plus 1. They naturally pair up together. And this is n to the first power. This is a version of n to the first power, so they easily match up together. Now notice I haven't broken any rules because this times this times this is the same as this times this times this. It's just a different order. So we're just helping our eyeballs make sense or organization out of the chaos of that limit or that limit. If you look to this next step, the limit just got even easier, but how did that happen? What I want to do is I want to go through this, now that I've organized it nicely, and kind of analyze each piece by itself, ignoring the other pieces. So concentrating on this first piece, this divided by that leaves me with x to the first power. That's really the same property that says when you're dividing in the exponent world, you subtract. So 5 minus 4 is 1. N plus 1 minus n is 1. That's how I get that one. For that next piece, as n approaches infinity, if I compare these tops and bottoms, what I'm going to end up having is a 1, because the strongest exponent in the numerator is 1, the strongest exponent in the denominator is 1. That means as I approach infinity, this plus 1 doesn't really matter. and as I compare an n to the first over n to the first, it trends to a value of 1. That's how I get that value inside there. And actually, since I've already applied the limit to that, I could take that outside of the absolute value, and that would be fine as well. For this last part, basically I have a similar type of thinking as over here. If an exponent in the denominator is 1 greater than the exponent in the numerator, then the denominator ends up with an exponent of 1. That's the same algebra concept as you see right there, just in a slightly more complicated form. That's how I'm getting the 1/2. So it's no small task to get from this original limit all the way down to here, and from here I can even simplify it further, and I can say this thing turns into this. Well, notice what's happened here. As n has approached infinity, all my n's have disappeared through this type of logic, but the x has remained. So now what I really have to do is I have to say, what in the heck would make this be less than 1? Because if I can make this less than 1, I've satisfied the idea of convergence with the ratio test. And here's where the old algebra absolute value stuff comes into play. If I want this thing to be less than 1, then I should really write this thing less than 1. And I need to go ahead and write that out in inequality form, and now I can solve for x. I have my interval of convergence. And if I want to look at it visually, then I can see that interval right on this number line, and maybe it helps me spot the center of convergence a little bit better and identify the radius. Now there's one thing here that you need to be very, very aware of. I'm purposely right now excluding the step of checking the endpoints. We're brand new to this, so there's no reason to add another moving part to this, but in a future lesson, we're going to take a look and examine closer the -2 and the 2, because it might turn out that it's not a soft bracket, it could be a hard bracket. A final word of friendly advice: anytime you're using the ratio test to do an interval of convergence calculations, be very precise with writing either this as your first step or this as your first step. It's okay if you go straight to this, but you need to show that it's a limit, you need to show the absolute values and so on. Very frequently I see this first step as a partial credit point if you're taking an AP test. This has been an introduction to the intervals of convergence using the ratio test, but we're going to add on a few more bells and whistles in the next couple of lessons.